My name is Eyal.
And my name is Shai.
We are graduate students of Tel Aviv University Faculty of Engineering under the supervision of Professor Giris and Professor Maro. In the following video, we would like to present our project called ARCADE, which stands for Accurate and Rapid Camera for Depth Estimation. Our project is based on groundbreaking research that enable integration of depth information into the image acquisition process of a standard camera.
Using this depth information in coded images, we then use a deep neural network deployed on an NVIDIA Jetson TX2 to generate depth images. Passive depth estimation is a serious challenge. While stereo cameras are a well-known solution, achieving passive depth estimation with a single camera becomes complicated and generally results in very deep neural networks not suitable for real-time and low-power applications. In our project, the depth estimation challenge is engaged on two fronts simultaneously. Both the optics and the post-processing work in tandem to achieve the final result. The light entering the lens holds depth information on every object in the phase of the wavefront. This information is lost in conventional imaging systems. Our solution is based on computational imaging, a method that manipulates the image acquisition process in order to encode this depth information in the captured image. In a conventional imaging system, all colors respond almost the same way to depth changes in the form of out-of-focus blur. Our imaging system introduces a unique dependency between depth and color response. This dependency is achieved using a phase mask, which is a very simple and low-cost micro-optical element that can be easily added to any manufactured lens. This innovative imaging process encodes subtle depth cues in the acquired image.
We then use deep neural networks to extract the depth of every pixel in our image by interpreting the out-of-focus blur cues. By doing so, we achieve depth segmentation of the acquired image. We start with generating a classification network that is trained to identify between 15 different depth slices. For this network training, we use artificially generated data, which consists of various texture patches blurred by different depth-dependent kernels. Since our goal is fast processing time, we use a relatively shallow network. We then convert the classification network to a fully convolutional network, which associates every pixel in the image to its depth slice. This modification is done by turning the fully connected layer into a 15-output convolutional layer and adding a deconvolution layer as well. We train this network using artificial images of 3D animated scenes. The network we train classifies over 93% of the pixels with up to one depth slice away from the actual ground truth. Finally, we use TensorRT to optimize our trained model for deployment on NVIDIA Jetson TX2. By doing so, we achieve an inference time of less than half a second for over QHD images. Here are a few examples of our results. To conclude, this project proves the concept of an NVIDIA Jetson TX2 based system that generates depth images while using a single camera and without using any expensive optical or mechanical hardware. The great achievement of this project, as we see it, is making depth imaging accessible.
Since the optical element we manufacture and use costs next to nothing, every machine powered by an NVIDIA Jetson TX2 can now generate depth images with negligible additional cost. By achieving this, we make depth images acquisition accessible to many markets, such as sport analytics for all athletes at any level, do-it-yourself robotic kits, affordable blind assistance products, and even collision avoidance systems for all budget cars and commercial drones. We hope this project will enable depth imaging for various existing applications and may also inspire the development of new ones. Thank you for watching.